Good morning, everybody. Looking good. Hopefully you're looking good. Welcome to another wonderful morning good morning, Ruben, of Chem 1105 with your host, me, Dr. White. Now, before I do what I promised yesterday, which was to tell a neat story that one of your colleagues asked me to tell, a couple things I want to talk about. First of all, if you don't know how to use this with scientific notation, you're going to be in big trouble in test two. See me my office hour tonight or next Tuesday after lab. I'll stick around. Anybody needs help figuring out how to do multiplication division with scientific notation, please stick around. All right, that's number one. Number two, number you haven't been handing in labs. There was a lab due yesterday. I'll put out an email today or tomorrow, probably tomorrow. I've been busy today. I've been working since 6:30. Well, it's been a busy day already for me. I will put out an email with an amnesty program, lab amnesty. All of you who have not handed in past labs, you'll have until next Tuesday to get them into me. If the link is no longer available on Blackboard, I'm going to go back and change it, make them available, upload it. Starting next Tuesday, I will enforce what's in my syllabus. If you don't hand the lab in on time by Tuesday, you're going to lose 2 points. If you don't hand it in within 8 days after next Tuesday, you'll get 0 points. Right now, we've done 5 labs, so that means there's 7 more. You lose 10 points, that's 70 points if you don't hand your labs. Guess what? That's going to really hurt your grade. You don't want that. I don't want that, but I still don't want to get a lot of labs tracing them down. So please get them in on time. All right. Now, let me do this. Let me go over here. And something I should have shown a while back, but I didn't. Let's see if I have it. I do. All right. Liberty Mutual seems to be everywhere.
Customize and save with Liberty Mutual.
I can shut out the volume. All right, thumbs up, people. Do you see YouTube? All right, everybody should see Brainiac alkali metals on their screen. Do you see that? Thumbs up, people, the fire. Anybody out there today? Thank you, Taylor. All right, let's go full screen and turn on the volume and enjoy.
Whether you've left school or you're still at school, you can appreciate the sheer fun, mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. The odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate. Press. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
Now, 2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes. That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard. Cesium, the emperor of alkali metals, particularly nasty to go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in the bathtub.
Fair enough, mate. I'll leave it to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. But still, there you go. Today's lesson.
Never mixed alkali metals with water.
Did you know detergent leaves behind bacteria? Add Clorox laundry sanitizer to every load to kill 90.
I hope you enjoyed that all. You can see I'm happy. I'm an organic chemist, and we like blowing up things when we were young. And now for the story. First of all, I do have to admit that another great TV show, The Mythbusters, proved the actual explosions that Brainiacs did were sort of faked. But in real life, if you use larger amounts of maybe this much more of the alkali metals, you get that effect. Now, for the story. Many years ago, long time ago in a galaxy far, far away, many years ago, at a high school in Skokie, Niles West, which some people you might know went to, they had a thing called Science Seminar. And Science Seminar was students who were really good in science were picked to be in Science Seminar. And this is long before 9/11, shows you how stupid schools can be. And if you remember a science seminar, we had our own laboratory and free access to the school's chemistry stockroom, and we were unsupervised. During study hall, you went to the science seminar lab. You didn't have to go to study hall. And we did some amazing things. And one of the things, well, I wasn't really there. Yeah, right. Anyways, somehow some guys, a couple of them, decided to steal about 3 or 4 pounds of sodium metal. And early one Saturday morning, those 4 guys went down to a beach near Northwestern, Lake Michigan, with the sodium metal and slingshots. And those guys took big pieces of sodium metal, shot them into the lake, and all of a sudden, like you saw in the video, boom, they blew up. It was a lot of fun, I guess. But anyways, this is about 6 a.m. in the morning, and along comes a policeman. He stops, gets out, and comes to us and says, "Boys, what are you doing?" He says, "Oh, we're investigating the reaction to alkali metals with Lake Michigan's water." He said, "Okay, but be careful," and left. In 9/11, they would have been arrested. And that's the sodium story. They weren't really depth charges, but with the larger pieces, like you saw in that video, those boys, saw in Lake Michigan. It was quite awesome. But anyways, remember, alkali metals are dangerous. Be careful. I personally have worked in a lab with lithium, sodium, potassium. Lithium isn't that bad. Sodium isn't, you got to be careful. It will catch fire in a humid day. But potassium, that separates those who should be chemists from those who aren't going to be chemists. All right. I hope you enjoyed my little story there. And to the colleague who, I might as well, Ruben, that's the story. I guess whoever it was told you. I hope everybody enjoyed it. Oh, I can do this. I'm gonna, are you done? But the question I'll ask is, did you enjoy the story? Yes, you did. No, you didn't. All right, looks like most of you did. But now it's time to get back to chemistry. And let me open up 2 more files that I didn't open up. All right, we're talking about the mole, and the mole is the chemist counting unit. And let's do one more mole problem. First of all, I gotta get my pen. All right, remember, 1 mole of a compound equals Avogadro's number molecules of that compound. And why don't you try this on your own first? Just set it up if you don't have a calculator. First of all, what are you being asked to find? What are you given? And then use your good buddy, your good friend, unit analysis. Your turn. All right, looks like everybody's done, so I'm going to get to work. And the first thing is, what are you being asked to find? Molecules of KOH, which is potassium hydroxide. I'll teach you more later in the semester about KOH. And you're given 3.333 moles of KOH. So how do you begin? Well, this is the only number I have to work with, really. So I'm going to work with it. Profound. And don't forget to write the units. Now, if I had some sort of magic ratio, what units do I want my answer to be? Well, we figured that out right there. Molecules of KOH. And where do we get these numbers that go in there? Well, it's time to use your good buddy, your good friend, unit analysis. I love that whistle. And whatever you're trying to get to, the units go on top of that ratio. And what, excuse me, getting all choked up over this. And whatever you're trying to get rid of goes underneath. And now I'm going to write that in. And where do I get these two numbers? From right here. 1 mole of a compound equals Avogadro's number of molecules of that compound. And now, before I continue with my calculator, notice moles of KOH are divided by moles of KOH. Anything divided by itself equals number 1, means it's canceled out. So this cancels out this. I'm left with the right units. Yay! And now I can go to my calculator. By the way, this is 4 significant figures. This is 3 significant figures. And my answer, therefore, should be the lowest of those 2 numbers, which is 3 significant figures. So now I'm going to go to my calculator and put in 3.333 times 6.02, blue key double E, 23, hit enter. My calculator gives me this number. But this is a lot more than 3 significant figures. How do you round that off? Keep the 2, keep the 0, keep the 0. Those are my 3. Use the 6 to round off. Is that 4 or 5 or higher, or 4 or less? Hopefully I'll pick 5 or higher. I drop all this, increase that by 1, which means 2.01 times 10 to the 24th molecules of KOH, potassium hydroxide. And that's how you do that. Now, I mentioned it, I believe yesterday. If you were to do this problem and you got the wrong answer, but you have all this work showing that hey, I know what I'm doing, I just made a math error, I take off 1 point. If you put down the wrong answer and show no work, I give you 0 points. So on my test, and which is one of the reasons I do not like multiple choice, because you can't give partial credit. Say somebody pushed the wrong key on their calculator, you've lost 5 points. That's not right. And therefore, it pays to show your work. All right. Let's move on. Let's talk about molar mass and what is the molar mass. Now we're talking about compounds such as, oh, I'm getting all my voice, such as water. what's the molar mass for a compound? Say water. It's the sum of the atomic masses of all atoms, and that is the molar mass. Now, this is important. Your instructor will most likely call this, because this is how I learned it, molecular weight, and I'll abbreviate it MW. So I won't use the term molar mass, I'll use molecular weight. And now I also have to be subtle. You should know this. Again, molecular weight is the sum of all atomic masses of all the atoms in the molecule. Now, let me open something that I didn't open up yet, and I better do it now. All right. Thumbs up, people. Do you see important information? Test 2 important information on your screen. Thank you, Mackenzie. Thank you, Gabby. All right. If you notice right here, you don't have to memorize this. As I said, I've cut down on the memorization in my class. You have to know how to use it. And it says the molecular weight of a compound is the sum of all atomic weights in that compound. And that you should know. So let's have some fun with this. It's practice time. Time to calculate the formula mass, or I better say, on a test, I'd more likely say that. Let's do water. And before we do that, I have to open up the periodic table. All right, let's take a look at this. Remember, I mentioned it before. Well, I don't know if I did mention it before. It's time for a gift from Dr. White, me. It's a little gift, but it actually is actually much bigger gift. On my test in my class, you will use all atomic weights to 3 significant figures. On test 2, it will say underneath your name, first of all, please use proper significant figures for all calculated answers. And then it will say, please use 3, that's 1, 2, 3 significant figures for all calculated molecular weights, or just please use 3 significant figures for all atomic weights. So let's look at the periodic table. Now, water has hydrogen and oxygen. Hydrogen on the table, 1.008. How do you round that off to 3 significant figures? You keep the 1, keep the 0, keep the 0. Use the 8 to round off, that's 5 or higher, you drop that, and the number in front is increased by 1. So the 3 significant figures, hydrogen is 1.01 atomic weight. Now, oxygen is 15.999. The number underneath is the atomic weight of an element. And I'm going to let you have some fun. Why don't you first try and round that off to 3 significant figures? Go. I like that, go. Time's up. Hopefully you all came up with 16.0. How do we do that? Keep the 1, keep the 5, keep the first 9. The second 9 you round off. That's 5 or higher. So the end 2 9s you drop, and the last 9, 15.9, you increase by 1, which becomes 1.0 plus 15 is 16.0. And that's how you round it off to 3 significant figures. And let's go do an example. All right, so you have to find the molecular weight of water. Well, water has 2 hydrogens and 1 oxygen. Remember, what is the molecular weight of a compound? And the molecular weight of a compound is the sum of all atomic weights in that compound. Well, that's how I got 2 hydrogens and 1 oxygen. Now, the atomic weight, and this is how I will usually abbreviate atomic weights, for hydrogen is 1.01 to 3 significant figures. For oxygen, 16.0. So now I can say 2 times 1.01, because all the hydrogens, there are 2 of them, and that would be equal to 2.02. Now for oxygen, there's only 1, and the atomic weight is 16.0, and there's 1 times 16.0 is 16.0. By the way, 2 and 1 are exact numbers, in case you're wondering. Now I'm going to add these 2 together, and I get 18.02. I'm not done yet. Remember, the rules for addition with significant figures, you get the same number of significant figures to the right of the decimal point as the number you're adding, or the numbers you're adding that have the fewest significant figures. This is 1, this is 2. What's the smallest number? Hopefully I'll pick 1. So to the right of the decimal point, you keep the first and use this to round off. That's 4 or less. So the correct answer is this for the molecular weight of water, 18.0, using 3 significant figures for atomic masses, which is what we will do in my class. If you don't, I'll take off a point. And let's try ammonia. And ammonia has 3 hydrogens, 1 nitrogen. And if we look at the periodic table, nitrogen on the one you'll use for test number 2, 3, 4 in the final, notice it says 14.007. I'll let you try and round that off to 3 significant figures first. Time's up. Hopefully you pick 14.0. Keep the 1, keep the 4, keep the first 0. The second 0 you use to round off, that's 4 or less, so that and the 7 you drop. And hydrogen is still 1.01. and I'll let you try the rest of it. Remember, the molecular weight of a compound is the sum of all atomic weights. Your turn. If you finish early, please be patient. I try and give everybody time to do it. One of the bad things about Zoom and students who don't turn on their webcams is when I'm face to face, I can just look at the class and see when everybody's done. I also say when we're face to face, when you're done, look up and smile, but none of you, or at least most of you, don't have your webcam on. Remember, it's National Turn On Your Webcam Week for Dr. White. So turn it on. Yeah, that didn't work. All right, let's get to work. How do you do molecular weight of ammonia? There's 1 nitrogen and 3 hydrogens. Remember, molecular weight is the sum of all atomic weights in a molecule. And for nitrogen, the atomic weight is 14.0. For hydrogen, there are 3 of them, it's 1.01. Do the math, 14.0, 3.03. We add them up because it's the sum of all atomic weights, and you get 17.03. This is not the correct answer because when you add things up, for significant figures, you get the same number of significant figures to the right of the decimal point as the number that has the fewest significant figures to the right of the decimal point. This has 1, this has 2. That's 1, that's 2. Which one is the smallest number? Hopefully you all picked 1. So to the right of this decimal point, how do you get 1 significant figure? Keep the 0, use the 3 to round off. That's 4 or less. I drop it. And the correct answer is this. And let's do one more. Now, sodium has atomic weight of 23.0. Oxygen, we've already done. Hydrogen, we've already done. And now I'm going to ask you, what's the molecular weight of sodium hydroxide? By the way, the old name of sodium hydroxide is lye. How many of you have heard of lye soap? It was made using sodium hydroxide. And later, near the end of the semester, I'll teach you all about soap and how it works. Yes, that's chemistry. Actually, it's organic chemistry. All right, I think everybody's done. Let's get to work. Now, the sum of all atomic weights is equal to the molecular weight. And there's one sodium, I've got that here, one oxygen, one hydrogen. If I add it up, and let me write it nicer. And add all these up and watch that I don't make a mistake because I'm going to do this one in my head. I get 40.0. Now, remember, when you add something up, you get the same number of significant figures to the right of the decimal point as the number that has the fewest significant figures to the right of the decimal. 1, 1, 2, which is the smallest number. Hopefully I'll pick 1. So here's my decimal point. Keep this, use the 1 to round off. That's 4 or less. So the correct molecular weight for sodium hydroxide using atomic masses or weights, the 3 significant figures, is 40.0. And that's how you do atomic weights or molecular weights with atomic weights. And the question you should all be asking is, all right, why did I just learn that? What good is that? Good question. Thank you, Dr. White. Don't tell any psychiatrists I just said that. But anyways, I got 2 personality. No. Let's look at what's called in your book molar mass and element molar mass. The quantity in grams that an element equals in grams of an element that equals the atomic mass of that element. Next, there's molecular molar mass, and this is the quantity in grams and formula mass, the molecular weight of a molecule equals the formula mass of the molecule. Now, this is in your book, and it's not well written. Better is this. 4 elements. And before I go through this, I better do this. When I was a student, that was a long time ago, in the left margin of my notebook, if I thought it was important, I'd put a couple stars. And if I put IMP, that means I better learn this. But anyways, 1 mole of a compound equals the atomic mass in grams. 1 mole of a compound equals the atomic mass in grams. 1 mole of the formula weight, otherwise known as one mole of the molecular weight in grams, 1 mole of a compound equals the formula or molecular weight in grams. You should know this. Now, before you say, well, you said you're going to cut down on memorization in this class, and I did. And let's go back to important information. And here I have 1 mole of a compound equals the molecular weight of that compound in grams, and 1 mole of an element equals the atomic weight in grams. So if I wanted a mole of water, remember back here, we find the molecular weight of water is 18. So what that means is, if I said, quick, go to the lab and bring back a mole of water, how are you going to count 6.02 times 10 to the 23rd molecules of water? You can't. I can't. Anybody see the individual molecules there? No. but you can go to the lab and weigh out 18.0 grams of water, and then you'll have a mole. And that's also equal to 6.02 times 10 to the 23rd molecules of water. So one of the most powerful things I know of all chemistry is a mole with molecular weight or a mole with atomic weight. And therefore, let's look at the following. How many grams of water is and the question is, how many grams of water is 8.31 moles of water? So what are we trying to find? Grams of water. By the way, that G is grams. And that's the metric units of weights. You can do this in pounds too, which we do in the United States. But for my class, we're going to stick to grams. And what are we given? 8.31 moles of water. Now it's time to use your good buddy, your good friend, unit analysis. This is all I have to start with. If I had some conversion factor, what units do I want my answer to be? Well, we took the time to figure that out right here. I want grams of water. And now I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of this ratio. Whatever I'm trying to get to goes underneath. Hopefully you're getting the hang of this. And so grams of water goes on top and moles of water goes underneath. Now, where do I get these numbers? From 1 mole of a compound equals the molecular weight, and MW is shorthand, in grams of the compound. There, I keep on writing and I realize, well, what do you need here? 1 mole equals the molecular weight of, oh, we've got to figure out the molecular weight of water. The molecular weight of water is the sum of all atomic weights. And each hydrogen is 1.01. Each oxygen is 16.0. Add them up. Use significant figures. This is 1, 2. This should be 1. Keep the 0. So the molecular weight in grams of water is 18.0. Remember, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of water or any compound is the sum of all atomic weights. And here I get 1 mole equals 18.0 grams. Remember, when you have A equal B, you have 2 ratios you can write, and that's how I get those numbers. Now, before I go any further, I'm going to use my knowledge of unit analysis to say moles of water divided by moles of water. Anything divided by itself equals the number 1, cancels out. This cancels out. Oh, look, I've got the right units. And now I can safely pick up my calculator, clear it, put 8.31 times 18.0, hit enter, and my calculator gives me, let me move the video feed over here. My calculator gives me but this is 3 significant figures, and this is 3 significant figures, and therefore I'm going to let you round. Ooh, this is a hard one. Why don't you try rounding this number off to 3 significant figures? I'll give you 3 seconds. I'll give you a few more. Go. Time's up. Keep the 1. Keep the 4. Keep the 9. Use this number to round off. It's 5 or less. You increase this by 1. That increases this whole thing by 1, which is 1.50 times 10 squared grams of water. And that's your answer, which I'm going to write up here so you can see it better. And that's how you do it. And again, remember, 1 mole of a compound equals the molecular weight. I didn't do one for elements. And this is how you use unit analysis to do that. If I look at the clock, I'm just about out of time. Now, important thing, don't forget, get your lab in. You don't want to lose points. I don't want to give you zeros. If you don't know how to use this with scientific notation, see me tonight, my office hour, or next Tuesday after lab. And come to think of it, let's do a cliffhanger. If you know what a cliffhanger is in movies or TV. And the cliffhanger is, on Friday, I'll explain why Dr. White, me, and people my generation are hooked on 3 significant figures. We are. But with that, I'm done. I'll see you on Friday. Gang gesund, be healthy. Bye now. Don't forget your shot and don't forget to wear your mask.